Cool. So the basics of profiling. So where did this talk come from? About 2 years ago. Again, time blends. I was at CPPCon. I was at my home at CPPCon. That's me in my Stockholm apartment. In 2020, I was talking about how I made some optimization in the concurrency model of one of our other games at Paradox. I'll go back to my games in a minute. To make it start faster. And people got very excited about this slide because it showed like a small profile of my game. And after I sat down on the virtual lobby, I got a full table of people coming like, mate, how does that work? Like, how did that happen? And basically we ended up doing a live demo of the profiling tool. I think I live profiled the game for the audience. I don't think there was any recording unless someone secretly recorded me and never told me about it. But I realized there is a need there. Like, I think people are interested into that. So I guess I could start with a quick show of hands. Like, who here uses profilers, like, commonly? Oh, cool. Yeah, half of you, maybe? That's good. That's good. And for the other one, you're exactly my audience. And for the ones who do, well, I hope I can still teach you a thing or two. So basically, the talk 2 years ago was, hey, here is how I made things fast. That was the showcase. Today it's like, hey, here is how I found out that it was actually bad, and I could do better. So hi, I'm Mathieu. I'm a tech lead at Paradox Development Studio, where I make a game called Hearts of Iron, which is about World War II, which we'll see in a minute because that's my basis for the live demo. You can find me at all those social things. You will notice that not two of them have the same identifier. It's a feature, not a bug. We're hiring, by the way. So if you're interested in coming to Stockholm, you are absolutely welcome to do so. In 5 years, we'll give you your EU citizenship back. Anyway. That's a low blow. Sorry. I had to do it. So this talks about profiling. The tools for profiling, and building an intuition about profiling. Because there's a lot of intuition that comes up when you start profiling things. And I'll get down I'll get back to it. But let's start with some very basic theory and words, just to give you a basic idea of profiling, why profiling, and what is it about. So let's start with the code. That's probably the most overused code I ever seen in any talk, which you probably have read too. The real problem is that programmers have spent far too much time. Sorry, I don't have a feedback. Worrying about efficiency in the wrong places and at the wrong times. I tried to figure out who wrote this quote. I couldn't because Tony Hoare, Distra, and I think Knuf keeps sending the authorship back to each other. All I can say that it's probably old, like 70s, 80s, maybe something like that. And I think it's just even worse today. Like figuring out why a program is slow is very hard, and that's why if you try to focus on an area just by intuition, there is a chance you will be wrong. And you can try reading the code and figure out like, oh, okay, just by reading it, I can tell where it's going to be the bottleneck. And to be fair, with some experience, you can get reasonably strong at this. But there's still a lot of way you can be wrong about that. And going back to the fact that this code is from the 70s, bear in mind that when they wrote that, they were talking about computers that can't guarantee that they are going to actually execute each of your assembly lines or C lines in order, without a lot of very hidden mechanisms. They didn't have problems like we have today, like with out-of-order execution, caches, and all that stuff. Like, today's CPUs are stupidly complex and hard to reason about. That could be a whole talk about itself. Like, every time you look at some assembly code and you say, oh, that's probably what the CPU is doing, you're probably wrong. And there's like 2 Intel engineers who can tell you what's actually happening in what order. It's a computer inside a computer. You cannot, it's very, very hard to reason about it. There's a few abstractions that can help, but as they are, they're abstractions, so they are a bit leaky. So yeah, measurements. If you remember my lightning talk from yesterday, I mentioned a bit the history of measurements. We're going to get into it a bit more today. So yeah, the idea for profiler, that's basically a tool to help us programmers to measure and reason about the performance of our programs. So yeah, basically if you try to optimize something, you have an application and you wanna optimize it, you wanna make it faster. I mean, that's usually where you optimize it. You wanna make it faster, so what do? You start by measuring, of course. Always start by measuring. Get a measurement, like, okay, this is how fast it goes, or this is how long it takes to complete, or this is how many FPS I got, whatever your metric is. Then, are you happy about this number? Maybe you are, and this is a very important step. I'm the first one to be very easily falling in this rabbit hole, or like, look, I can make those numbers a little smaller again. And you can spend your life doing this, but at some point you need to say, okay, it's fine, it's good enough. That's the target metric I wanted. We can stop and focus on something else for a bit. And then if you're happy, it's great. You're done. And if you're not happy about it, well, you try to optimize it, find exactly where you can improve some bits of your program, and then you recompile and try again. And at some point, you're done. That's basically the idea. So profilers will help you in two steps. They will help you when you're trying to optimize. And I guess they might also help you when you're measuring, because even if maybe profilers are not the best tool for measuring performance, I don't think they're that bad. And I found myself using them more and more sometimes to just figure out, hey, is this version better than the previous one? It's not the only way. It probably should not be the only way you do it, but it's a way that is acceptable, in my opinion, to figure out if you're doing better than what the previous solution you were submitting. So, excuse me, I need to remember my slides. Yeah, so basically what I said, like profilers is one of the tools you use when you're trying to optimize a program and figure out how it's going. It's again better used to investigate where to improve the performance than to measure, but you can use it. And like I said, you can use it to reason about how efficient the thing is. For example, you can see like, oh, it doesn't show up in my profiler anymore, which might mean it's much better. Might mean you have actually just displaced the problem and it's still slow as it is. So again, good to tell if one particular block of code you're trying to optimize is now better. Not always good at telling you that the whole program is now faster. For example, if you remember the couple slides at the beginning when I was talking about optimizing the startup speed of my game a couple years ago, I ran into several places when the big bottleneck on the top of my profiler was a mutex. I removed it, and the game did not start any faster because there was another mutex or another blocking call somewhere else that was just blocked by the mutex before. Yes, the bottleneck was gone. There was just another one now, and it wasn't any faster until I fixed all of that. So yeah, you can do some of measurements with it, but don't entirely rely on it. Still run your application and see, is it actually faster, or is it just faster in your profiler? So yeah, you can do a lot with a profiler. You can identify hotspots and bottlenecks. You can visualize the execution timeline. And I think I will insist on this one a lot because I found a profiler 2 years ago that is really better than everything else I ever used before to visualizing execution timelines, especially for games, but I think for other applications probably too. You can collect and compute a lot of metrics. And by a lot, I mean a stupid amount of metrics. More metrics that you will never know, especially if you start using advanced profilers like vTune and other that. You will have to learn a bunch of CPU stuff to be able to figure out what those metrics actually mean. Very helpful, but maybe not for everybody. So there's two types of profiling. There's sampling and there's instrumentation. And if you get confused by the two terms, do not be afraid, I was too. To the point that until a change I made in my game a couple months ago, the macro to instrument code was actually code sample because I could not remember which was which. Anyway, how does sampling work? Sampling is the easiest of all. You basically you use the debugging facility of your operating system. You attach to a process. Periodically, you just pause. You look at the call stack. You recall where you are. And if you do that often enough and long enough, then you can do some sampling, mathematical sampling, and then you get a bunch of averages. And it says, okay, on average, your program, when I pull it, is there. And that gives you a rough idea of where your time is spent. It's very easy to do. And yeah, the very important thing to remember, results are statistical averages, which comes with some caveats. An example tool is vTune. It's not the only one. That's the one I used for a long time. I tried Superliminal recently. Wasn't very convinced. But again, I'm more and more of a fan of instrumentation profiling instead. But we'll get back to it. There's still some good things to get from this. So the big advantage is If you don't want to do anything to your program, you just have a program and you want to know where the bottleneck is, or if you want to get some idea of how it's behaving internally, you just install a profiler, run your program, attach the debugger, attach the profiler, and you're mostly done. As long as you have enough debug info to get a stack trace, that's good enough to get something out of a sampling profiler. You don't need anything else. And more importantly, you don't need to recompile your program. You don't need to tweak anything in your program. It's as long as you have the PDBs on Windows or the debug symbols on Linux, it's basically good enough. And even without all the debug symbols, just the stack trace, good enough. You can get something out of it. It's really plug and play. Again, works out of the box. You can sample a program that is not yours as long as you have enough things. I've done it once or twice just because I was curious. Of course, since it is based on the stack trace, if you have inline functions, there's a good chance that they will completely disappear. So, for example, if you're using containers that usually get most of their container and algorithms and templates, which usually gets completely inline on the call site, you will not see it as one call stack. Like, for example, you will not see that you're spending a lot of time in a given algorithm or a given container. It will be basically spread around all the places that uses it because it's inline in the call stack. So if, for example, you have a bug in one of your containers that is very slow for some reason, you broke your map or you broke your vector or you have an algorithm that is not as fast as it should be, you will not see it as, oh, everybody's calling like this map.find and it's taking forever. You will see every call site separately as being a bit slow and it's harder to see in the whole outline of the program. The other issue, but we'll get back to it, is that it's based on, as I mentioned, on statistical averages, which means if you have an outlier that is slowing down your program every X, it's very hard to see. Classic thing is you're making a game, you have X frames per second, and every X frame per second, you do a special computation that is usually not done every frame, and that spikes the frame rate. You will have a hard time seeing it because it will just be lost in the noise of statistical analysis and just everything being the averages. Instrumentation, on the other hand, it's you had some hooks in your code to say, like, I was there. And every time you do that, the instrumentation library that you attach to your program will just record it somewhere. And once your profiling session is over, it will be able to reconstruct the stack and show you a bunch of things. So you can use that to get averages, of course, because you can just agglomerate. But more importantly, you can provide some kind of form of a cycle. For example, in video games, you can say we are doing frames. But if you're making like a network processor, you could say like this is a request, that basically the basic unit of the for loop of the main for loop of your program or whatever is your main loop. You can just time to each one of those, and each one of those you can see exactly which bits took the longest. So you're not, as I mentioned before, you're not going to get completely sidelined by statistical averages. If you have one request that is 20 times as slow as the 200 others you do, it will show up very quickly, and then you can see, hey, what's the difference between this one and the others? So yeah, exactly what I just said. And also, usually not affected by inlining as long as you have put a label in your inline function, of course. A good example of it is Optick, which is the one I'm going to demonstrate for this talk a bit further from here. So, of course, it has a cost. You need to add a bunch of usually macros in your code at tactical places to figure out, to give the instrumentation some hints of, hey, this is where I am. This is the place that I want you to record. It's not going to record every frame or every function. It's going to record whatever you ask it to do. So usually you put it in like places that you're interested in. The advantage is since you are deciding it, you can put it in a way that makes sense for your business logic rather than the actual logic. It doesn't matter if there is 1 or 20 function called down the line. It can be seen as one operation, for example, because you decide where the boundaries are. You can also add metadata, which is probably my favorite thing, or one of my favorite things. Every time you say, oh, this is a specific frame or a specific like block, you can say, oh, I'm going to add some business metadata. For example, in my game, I mentioned a bunch of things like which country is it computing the world for and stuff like that. And that may allow you to see something. Like, for example, you log the type of request it is processing, and you realize that this one is very slow. Or if you can log you can put the client name or the client ID and say, hey, it's weird. Like, every time this client ID is there. Basically, it helps you see extra correlations that you wouldn't see otherwise, because that's just a stack trace if you're not having any of those. And the more important part, you can fall back on sampling, especially with Optick. You can say, oh, instrument this thing, and every time you're out of your depth, just use the good old sampler and give me a sample average of whatever happens under this frame. And that means you can have both in the same place. And usually what I do is that I start by adding a bunch of macro in a few places. And then when I start thinking like, oh, this area is not very well defined, it's just a big blob and I don't know exactly what's happening under, I look at the sampling view of that and I'm like, those function seems to come up a lot. I'll add a few more macros for those ones. And that helps me like define a bit more finely what I want out of it. It has build implications, of course. So it means you need to add a third party to your build. You need to have it included in your in all your file, and you need to link to it, and then you need to ship with a DLL when your program goes to release, which, depending on what you're doing, may or may not be possible. The thing I'm looking at right now for my company is that I want to ship the DLL and the thing as long as it's a beta build or a test build. And if I start making a release candidate or an actual release build, I will strip that down. Although I have been considering keeping it, but we'll see. So, just like this is the slide if you're following at home and you just want a quick reference about the difference between both that I just explained. Sampling is probably way easier to set up, but I think instrumentation is more rewarding down the line. But I guess this is a lot of theory, so maybe you want to see some practice now. Like, how does that actually work? So the first thing you should do is, of course, set up some kind of scenario that you can reproduce, right? Because you're trying to analyze the performance of something. You want to measure it, and if you want your measurements to have any sense, you should have some measure of reproducibility. If you measure the same thing like 3 times and you get completely different results, then by definition, whatever you try to do to improve it will also be impossible to correlate and say, oh, it's actually faster or slower. You can't do that. So yeah, you set up your scenario and then you measure the performance. And if you and then you define an objective. That's the happy part I mentioned in my previous slide. You need to define an objective because you can be there for days. I've been there for days. Don't be like me. At some point say, yeah, that's good enough. I think that bit doesn't really need to be looked at more. Which tool should you get? I would say I recommend instrumentation from the get-go. I know you have to add a library to your build, blah blah blah. But you know, I'm the build guy. Sometimes I talk about package management on my off hours. I'm not afraid of it, and honestly, it's not even that bad. It's one library. You just add the include dir, you link it at the end to your exit, and you put a DLL next to it, and you're done. It's not the end of the world. If really you can't, sampling is cheaper to start with. But I would say there is some kind of investment value to having instrumentation support in your program, because those macros will help you over time. At first it's a cost, but as you find more bugs and sample more things, you will just add more and more to the profiles, and then the next one will have that for free. Like the next guy coming after you trying to profile the application will just get all of that metadata for free, and that's a big value in my opinion. And again, it's really not that expensive. So demo time, and this is the time when you have to bear with me for a second or 10, because this potato clock is going to try to run my game on minimum settings, and we'll see how that goes. So this is my game. You have a special build just for you that I made, which is basically the release build that we released like yesterday, I think, except I have built in Optick. So the thing you're looking at, even if it's in French, is that I'm running this in admin mode. Why? Because if you're using Optick, the sampling is part of your program because it's in the Optick lib, so you need to be running in admin so that the debug sampling libraries can be attached to your program and start. So let's watch a loading screen together, please. Maybe. Just give it a sec. We don't have a splash screen. There we go. Ta-da. So yeah, this is Hardware 514. It was released in 2016. June 6th, we released on D-Day. That's kind of the whole theme. It's about World War II, 1936 to whenever you want, but we suggest you stop at 46 because we don't really guarantee performance or anything really after that date. Most people stop earlier. Some people play crazy mods that allow them to play all to the modern period. I don't know why they do it, but you know, If you want to do it, you can. Modding is basically or bread and butter. Yeah, so you can play any country in the world, and you play your country through World War II in terms of politics, war, production, infrastructure, logistics, a bunch of other things. That's not really important for today's demo. The important bit is that we're going to profile it. And then I can see the performance looks terrible because I'm running on this machine and not because there's something badly optimized in my game. We're in the UK, so we'll play as Stanley Baldwin. Apologies for the shaders. I had to put minimum because this is playing on an Intel GPU and it's really bad. It is really bad. Because our shaders are really not complicated, right? Like I'm not gonna say we're great at graphics, but I'm gonna say what we do is really stupid and dumb. And any normal GPU can crunch this, no problem at all. Unless it's an integrated Intel GPU, then not. There we go. This is the UK in 1936. There's a lot of things you can do, but look at this. We have an in-game profiler that I added a couple. Yeah, if I say enable collection, you can see 22 FPS. That's just brilliant. I'm paused. I'm not even running the simulation. The game is paused. Nothing is happening. So it's just rendering. Render as fast as you can. 22 FPS is the fastest you can come. 23 millisecond render time, great stuff. But it doesn't really matter. Again, what's important is that we can look at the profiling of this. So I'm gonna start. I'm gonna lower the volume because you don't want to all get deaf by the theme. If you want to feel at home, I have a bunch of soundtrack with like Churchill speeches. If I'd just like to ease some of you. Come on, I'm sure I clicked this button. Did I? Yes. Okay. Yes, it's opened somewhere. Probably need to alt. Yes, and it's on the wrong screen. I'm gonna fix this. Hi. So Optick, subtitle at the top. What the hell is going on? Which is exactly the question. What the hell is going on? You are like, oh, it's slow. What the hell is going on? So you click on the record button here, and you'll see it's gonna start capturing a bunch of things. Come on, please don't jump on me. Oh no. Yes, it's working. Yeah, we got about, anyway, let's get 60 frames. Anyway, that should have taken a second, technically, if we had 60 FPS, but we don't. Okay, cool. And then we'll stop here. That's a very simple capture. The simulation of the game is not running, so the only thing you'll see is basically the rendering of the game. As soon as it's done. Come on, serializing call stacks. There we go. Perfect. Brilliant. Why do I have this open twice? Oh, okay, it doesn't matter. So you will see a timeline of all the frames you're rendering. You can see that some of my frames are taking 200 milliseconds to render, which oh god, it's slow. But that drives the point, right? You can see a timeline of every of your frames, and this is a timeline of the whole program. I think I can do. I can't do. Can I do this? Yes, I can. You can see that this is every frame in a sequence. And if I zoom in a bit, you can see exactly what I'm doing. So for example, you can see that the frame starts here. I'm doing a bunch of stuff that is not part of the instrumentation. Then it's just doing the update the interface. It's processing the input. It's updating the map. Some common subsystem things. And then it's actually trying to render on the screen. And you have a timing for all of that. And you can see this is absolutely horrendous in terms of how long it takes on this machine, especially HAL-tabbed on a display that is bigger than what the native monitor is about. But you get the gist of it. And the thing I like, again, the thing I like and I find really cool is you have your actual timeline of the program. So for example, if I had one frame, I don't have one here, but if I had one frame that was really spiky, actually I can probably find one like this one, 268 milliseconds. For some reason, it's like, sometimes we manage to render in this, which is about 16 milliseconds, which is ideal. This is basically what we want. And sometimes we just go like, nah, let's go 266, and you can see that render to the object on screen somehow took 71 milliseconds. That's just the UI. I have no idea what's happening here, but I'll blame it on the computer. And again, I don't have details under this, but since I have enabled sampling, I can click function frame graph, and then if I pull this up a bit, like this, you will see that, even if I don't have any, I hope it's big enough for you to read, by the way. Even if I don't have any instrumentation data, I can basically get all the call stacks. So you can see, for example, that we're spending a full amount of time in some, that's the Intel driver, basically. Open adapter, blah, blah, that's the Intel driver. We're spending things. And there's a great recursive function here about a tree that is really inefficient, and I'm trying to rewrite it right now. You can get a pretty good view. This is entirely sampling, right? So it's not actually just your frame here. It's the whole program. Every time you're under that bit, what does it look like? That's a statistical view. That's what sampling does. But that gives you a very, I think, graphical, visualizing, like 2D representation. This is maybe the reason I like this tool so much. I'll show you a vTune in a bit. But to me, the main takeaway is this is very visual. This is very 2D. This has been made by people who like to do graphic stuff. And that really shows, because I find the other ones are just lines, like text and numbers, like basically they're matrices. This one is way more visual. If you want to see what is slower than X, you can just eyeball it and immediately says, hey, why is this thing so slow? I'm gonna make another one real quick if the machine gun is okay with it. I need to close the second. Oh, it opened 2 times. That's why. I'm gonna make one, but I'm gonna be harsher on the machine this time. Oh, sorry, I'll tap too early. I'm gonna delete this capture and make one that is worse. Cool. I'm gonna put the game in maximum speed, and I'm gonna run the simulation. Okay. So now the game is actually simulating a bunch of stuff, and it's probably gonna be even slower. Let's have a look. Connecting. It's using a local socket to access the program. There we go. Oh, we got 2 frames, 3 frames, 4 frames. It's usually not that slow, by the way. This machine just doesn't have the cores to be doing a capture at the same time as the game is running. It basically doesn't have the core to have the game running, and I'm asking more of it. Which allow me to segue to a thing. Capturing data actually might alter the profile of what you're profiling, especially if your program is really good at using all the cores you got. For example, on my home machine, I have 16 cores, and most of the time, even if the game is running at full speed and trying to thread everything it can, having a profiler thread on the side doesn't really matter much. It has an impact, I can see it, but it's minimal. If you look at this, you see all the red bits at the top? That's I desperately would like to get a CPU, but I can't because it's busy doing something else. That's a heat spike of your CPU. So if it's only green, that's basically like work time. If it's red, it's either wait time or you are trying to get a CPU, but there is none available right now. Like they're all busy doing something else. So as you can see, one of the big reasons this is so slow is that there's not enough cores available to do anything. It might also indicate that you're spending a lot of time in process, either inter-process communication, sleeping, banging on mutexes, that kind of stuff. But most of the time it's because your cores are busy doing something else. So you can see we're using multi-threading, contrary to what some fan seems to say. And I think TBB just put it 1 per physical core. Yes, so I have like 4 Walker threads. And yeah, you can see like in theory this thing should be using threads as much as it can, and it can't really because it's a bit slower. So we have captured a bunch of frames with horrendous performance time, but you can see that, I have a whole timeline of what my game update is doing. So you can see I'm trying to simulate an error. So I simulate the supply. I'm late, so I render a frame. Then I try to simulate the air. I'm late, so I render a frame. I'm late again, so I render another frame. Cool, and now I can try to update the countries. And then you can see the great hack we have to try to maintain frame rates when your machine is too slow to handle the simulation. It's much better in newer games. The old one is it's a bit roots, let's just say. But that gives you, I think, a good timeline of what's actually happening in your program and how the simulation is actually going. And with that, I can see a lot of things. But let's go back a bit to the slides. So the idea is that, you may have find it a bit overwhelming what I've been showing so far for the past 5 minutes. That's a lot of data. I'm used to look at this all day, so it's not as bad. But for the first time, it's a bit scary. And I think that's where the intuition and maybe like experience comes in. As you have been watching this a couple times, you start to get a picture of what it should look like. And then when something doesn't look like what it's used to be, you could say, hey, that sticks out. What's the deal with this thing? Domain knowledge is key. For example, like you look at my profile and you're like, okay, so it's spending about, I don't know, something like 160 milliseconds. Like this is those numbers. Do not just divide them by 10 for a normal machine, at least. Okay, you're spending 16 milliseconds simulating the supply system. Is that a good or a bad mark? If you've never profiled your application, you wouldn't know, right? But if you have domain knowledge, you can take a look and say, okay, this is roughly what it does in my head. Like there is no possible way to take 16 milliseconds or, oh, okay, no, 16 milliseconds sounds about right. It's even better because you can put it on a, you can try to compare it to other systems and say, okay, like for example, is it normal that it's like way fast? It's faster than a serial update of countries or like AI and a bunch of other things? Does that sound about right? Is the AI the most important part of our application? Yes or no? And like if you know what your application is about, and hopefully you know what your application is supposed to do, you should have a rough idea of which bits are technically supposed to be the more complex and doing the most computation. And so basically a lot of profiling comes down to you kind of had some assumptions about what was slow, and then you look at the profiler and something doesn't match. So either you're wrong, your assumptions are wrong, and actually this thing is really expensive, or actually maybe the implementation is bad, and yes, it shouldn't be taking that much. Or maybe there is something else at play. But it's basically that. You make assumptions about what your application is supposed to do. You look at the profile and you say, does that correlate what I expected? Yes or no? And find out what sticks out is really important. Again, a profiler can tell you what takes the most time in a given run. It can explain you why it's taking the most time, especially we'll see with vTune. It can give you a lot of metrics about, oh yeah, you have retired that amount of instructions. You have had like this or that amount of cache misses and a bunch of very other important metrics. It cannot tell you if it should be that expensive. It can tell you this costs 2 billion cycles. Is it good? Is it bad? I don't know. It's up to you to tell the profiler. Well, no, the profiler doesn't care. You can tell it what you want. I scream at it sometimes, but yeah, you can tell it what you want. It's important. It's for you. Okay, does that make sense? The profiler cannot tell you that. It's up to you. It can only tell you numbers. Then it's up to you to interpret them. Really. So it's a lot about hunting discrepancies again, like from what you expect. The more you do this, the more it's easy to spot a regression. I'll have an explanation just later, but yeah, basically, like you see what takes time. You have an idea in your head of what should take time. If something doesn't match, this is probably where you should be investigating. I used to have a demo, but I do not have it because okay, the build the game was still running. That's why it was so bad. Excuse me, I'll kill it. Hey, we managed to reach like 19th of January when I was in the background. That's nothing. It should basically be at the end of the year by now. But I'll tab again and go back to this. I had a bug that I discovered just before I initially made this talk. It's not in the build anymore, so you can't see it. But in the rendering pass of our program, which this one? Yeah, this one is good. If I can zoom in. Can I zoom in, please? Let me zoom in. And there we go. Okay. So you'll see that we do a bunch of stuff. And one of the things we do is that sometimes we need to update some textures we do for the map. For example, if a country takes over a province and a bunch of... There is a few places when we actually need to rebuild some textures as the game simulation progress. A bug I spotted very easily on the profiler is that each frame, this thing was being rebuilt. And my expectation is that it's supposed to be cached and only change every X amount of in-game day, months, eventually even. So even POSD was rebuilt every frame. And immediately it's going to me like, okay, there is something wrong. I just went to the code, looked at the condition that the cache was dirty. There was a bug in the Boolean. It was basically always false. And it was always true. So it was always rebuilding the texture. And that's the kind of thing that you can easily find if you're used to see a profiler. You're like, okay, this thing should only show up every 20, 50, 100 frames. It shows up every frame. There's probably something wrong with it. If you see, for example, a function called like we calculate cache data, or, you know, whatever, things like that. You're like, okay, by the name tells me this is not a thing that should happen often. If you have a function like in my game that I have like, that's called like on monthly update, and it's called every frame, you're like, that should be called every month in the game. Why is it called every frame? That kind of thing can stick out very easily and tell you like, oh, I think we have a regression here. So the most efficient code does nothing, right? So profiling can highlight useless computation, and then you don't even need to dive into metrics. Like I mentioned, the map thing. It tells me, hey, you're computing this every frame. And my thing is like, you shouldn't. And I didn't need to go into metrics of like, oh, how much branch prediction is about it, is there cache misses, or any very fine-grained metrics, or timings even. I didn't even need to look at how long it took. I just knew that it shouldn't be done at all. So there was no need to look at, hey, maybe I can make it faster. It's not about making it faster. It's about not doing it if you don't have to. That was basically like an easy win that I got from this. But yeah, when you're doing the first time you're profiling anything, try to assess the big picture. Again, if you know the domain, it's way better to know where to start digging. If you know roughly what your application loop is supposed to look like, then you can start saying, this is probably where I should start taking a look. A classic thing that is not only specific to profiling, just try to get the quick wins out of the way, right? Like if there is something very obvious that is bad, just do that, then start delving deeper. Again, you can go very far into profiling, especially if you start using like vTune or other like sampling profiler that gives you a lot of CPU metrics. You can go very deep into like this function in your logic has a bad cache miss rate. But before you get into that and the exploration of how your CPU or how your code can be optimized to match the CPU architecture, try to get the very big thing out of the way first. Like the complexity is wrong, the computation is called too many times, the algorithm is not the good one, the data structure is basically not the one you should be using for that kind of data pattern. Once you get that out of the way, you can start thinking like, oh yeah, the branch prediction on this F is bad. Maybe I should start tweaking it so that it's branchless or blah, blah, blah. But that's really advanced stuff. I think I got a comment from the original talk that said this talk was entirely pointless because I was not talking about like the micro optimization that Chandler did in his talk. And I would have to say, yes, this is a very good talk and you should watch it, but do not start by micro optimizing if you have like a whole application like this. If your application fits in a unit test, then sure, go ahead. Like you're probably already there. You have probably isolated everything else already. But for us people who have like a big application and what you have is, oh, the whole thing is slow, then yeah, like don't go to micro optimization at first. Just keep it last once you've done everything else. So I talked about micro optimization. I talked about changing data structure. I talked about algorithm. I'll try to explain a bit more. Like how do you analyze all of this, and basically some tips and tricks about what to look for. By the way, I have not done a lot of audience participation lately, so if you have any question, feel free to just like, tell me, raise your hand. We're all here in this room. You don't have to wait for the end. Just that also will let me just take a pause and watch the loading screens. So, profiling metrics. There's a bunch of things you can get out of a profiler. You can get the obvious thing like CPU time, wait time, system time. This is the very classic numbers you can get. I'm not gonna talk too much about system time today. That was more about my talk 2 years ago about like seeing the places when you have bottlenecks. I'll see if I can talk about it a bit. But another demo time, if you want to go more metrics, I'm gonna try to see if vTune wants to work. This is vTune. I installed it yesterday. So vTune is a profiler made by Intel. It's a sampling profiler. There is some instrumentation support in it. I tried. It's horrendous. Like the visualization is terrible compared to Optick. I just could not figure out anything. It just gives you very small bars with no labels. And if you had more than one level deep, it's just unreadable. So I just gave up and stopped using it at all entirely. I just, when I want to look at something very, very narrow, I can fire up vTune. It's free to use. It's on the Intel website. You need an Intel processor to make it work, I think. The basic things might work on an AMD, but every time you start going into metric, it doesn't work. There's a special offer right now from Intel. Their sign up and sign in page is broken, so you can download it without creating an account, which apparently is a problem. I made a bug report saying this is not a bug, don't fix it. Like, please. I don't know. Show of hands. Who likes to have to create an account to be able to try an application? Okay, for the recording, there was just about everybody in the room. No, nobody likes this. Why do you do this? Don't. Come on. But yeah, special offer from Intel right now. The sign up is broken. You can download everything without creating an account. Do it now. So you can hit configure analysis. It probably has a sampling app that come on. Uh-oh. This is why I should not have downloaded it a minute ago. Oh, it's actually working. It's just slow. Like everything on this computer. Oh, cool. You can see it's new because yeah, blah, blah, blah. Cool. All right, so you can launch an application or attach to an application. In our case, we will, actually, I need to relaunch the game again because it's running as root and Intel will not be able to attach to it. Sorry about that. You're going to have to watch the loading screen a second time, which will give me a small pause. So where are we? Here. You will also see that just because I have Optick support in the library doesn't mean I cannot attach a sampling profiler to it. There's absolutely no problem doing that at all. It's dormant until you activate it. I don't know about the overhead, which is a question I get often. I haven't noticed it. Like again, I run it again. All my local builds at the company for since I discovered Optick a year and a half ago, maybe. All my local builds have had Optick enabled, and I've tried to convince every other team at the company that every local developer build should have Optick enabled. Now I'm trying to push it to have it on every beta. I don't know yet if I'll push it for live. I'm considering it, but I'm not 100% because then I need to ship an extra DLL. Maybe in some cases it will be bad, but I'll get back to it at the end because I have some ideas that I want to explore with it and how much tooling I can build around this thing. I think at least for my QAs and maybe my beta testers, I will ship with builds that have that enabled on the side. But mostly for programmers, every time a programmer is say hey, I'm trying to work on this thing and I notice this thing is slow, I'm like, just Alt-Tab, start Optick, click record and see what's happening. And you don't have to wait. It's there, it's already in your build. You just have to click a button. If you have to tell them, oh, wait, change your config settings, do the rebuild all. On my game, it's only 5 minutes to do a rebuild all. It's not that bad. But even then, I will get I don't know, maybe I'll do it tomorrow. And we all know what happens. They don't. Cool. You like loading screens? We have lots of different pictures. I don't know if you've seen it all yet. Yeah, it's faster the second one because a bunch of files are in the Windows cache. If you have any question, by the way, while it loads, feel free to shout. Yes. Other alternatives. I think AMD is an equivalent. I can't for the life of me remember the name because literally all the CPUs I have here and at the office or Intel, I think I have one AMD machine on Linux, but I barely use it. So I don't know, but I think AMD is an equivalent. I mentioned superliminal before. If you want a quick sampling, superliminal will do the thing. If you want all the cool metrics that you get out of vTune, you'll be out of luck. Someone has described vTune as the nuclear option because it is. You will see it is not fast at making a sample, but it is very verbose. You can see just about everything you want. Let's go back to playing England again. Yeah, and then we'll start. Cool. Yeah, so if you want a lot of metrics, you will have to use basically the CPU vendor provided thing, which I think both Intel and AMD probably has one too. I can't remember the name. I can look it up after the talk if you want. Else you have other things like some colleagues used to use Very Sleepy, I think it's called. You can use Superliminal. There's a bunch of others. Again, I would say just in general, if you don't want the very specific fine metrics that vTune has, I think instrumentation gives me a better picture 90% of the time. Also, it's way faster because I just click record, stop, and that's really, really quick. Come on. Ooh, those are really nice shaders on there. Okay, cool. Here we are. So I'm gonna bump the speed again and tell it to run. It's running. Cool. Now I go back to vTune. So you can launch an app. I could have done that. Or you can attach to a process, which is what we will do. It's enter a valid process name. Okay, holy4.exe. It's gonna find it. Yes, and then you have a bunch of things. You have a lot of, like, this is vTune. This is everything you want and everything you don't want. For example, the classic thing is hotspots, which is a very classic sampling profiler view. Where are the hotspots? You get a top-down and a bottom-up view of your profile. I'll show you in a minute. You can see a lot of things. Parallelism is the one I used to, at the time for Stellaris, to figure out the waiting problems, because it records a lot more things about the wait times between the threads. So you can see, for example, if you have a lot of synchronization primitives being called. And then if you want to go nuts, you have memory access and microarchitectural exploration. I think those two require you to run vTune as root because it needs some extra privilege to be able to get the metrics. But you can get basically line by line almost. It can tell you like, oh yeah, this spent like X amount of time in the CPU front end, X amount of time in the CPU back end, and you got stalled by the level 2 cache. Which, again, if you want to delve into micro optimizations, great. If it's your first intro to profiling, you're like, what? Just leave it for later. So we'll do, actually, I think I'll do a threading one, because, no, I said threading, that's threading. Because threading also includes hotspots. Actually, you know what, yeah, let's go for hotspots, because I don't really have the capacity. Okay, cool. So you can use hardware thing events, but you need to be root. I'm just gonna go user mode sampling, which is the default. And you're gonna see how fast vTune is compared to, so it's going to try to start a program. It's going to tell you that it's starting an analysis. Are we getting there yet? Maybe. This isn't helped by the performance of the machine, really, but come on, you can do it. Come on. Don't let me hanging. Progress bars are great, right? I'm sure any minute now. So usually that step is quite fast-ish, because the next one is the one that is slow. But don't worry, because when that one is done, I can alt-tab and do something else, because this one is the one that delays the capture. Once the capture is done, then it needs to do some post-processing on the capture, and then you can alt-tab and just do other stuff in the meantime. Come on, it's trying to desperately boot up the capture driver, I think. Well, maybe they don't expect people to be developing on those machines. To be fair, I wouldn't expect anybody to be developing on those machines. This laptop was really great to do conference stuff. It's not so much great for this. Come on, don't leave me hanging. Else maybe we can try the demo app, because that will be good enough to get some numbers going. What's happening? Is it running? Is anything happening? Yeah. You know what? I think we'll have to... Collecting data, it says. Okay, cool. As I was about to cancel, let's get maybe 10 seconds. That's good enough. Okay, stop. So now it's gonna stop, and it's gonna try to resolve it. So what I'll do, I'll pause Hearts of Iron. You know, I'll just pause it for now to get a few calls back to the machine, so it can try to do this. And then it's going to try to finalize the result. So it's going to do a bunch of post-processing because it collects a lot of data. It's going to try to read the debug info. I think it's going to load the Microsoft DLLs for you if you have them, which also might take a minute. No, it's okay. It's doing the things. Downloading a bunch of PDBs. The Steam client. It tells you about the one that it doesn't have the data for. I did not bring the debug info for TBB, but it actually, it knows about TBB. That's one of the good things I liked about this, back when I used it a bunch more. It has all of TBB support already included. It knows if you're using TBB, it can do so. It can, for example, reattach call sites through like parallel 4s and other calls to TBB, because both are made by Intel and they have some secret macros in the code to talk to each other. So, for example, if you do threading analysis and stuff like that, it's able to reconstruct some stacks, even if you're basically doing like a parallel 4 in another thread. It can still find back the caller due to that, which is, I mean, it's a neat feature. If you're doing a lot of threading and you try to look at what's happening with TBB, this will give you a bunch more data. Okay, now it's the game overlay renderer 64.dll. There's so many DLL. I'll use this opportunity. Okay, we'll come back to it later, see if it actually managed to do it or not, because I don't want to. I'll stop the game entirely. This is the last live demo I had it. Once the capture is done, you can close the application that's doing it. It doesn't really matter for vTune. But for now, let's return to this, and we'll come back to it later, see if it's done. So your profile capture will probably show a bunch of things, right? A bunch of metrics, and you'll have some numbers. And the question is, what do you do about that? So if you start looking at a sampler view or a sampler view usually, or any kind of profiling view, and you see, okay, something has a high CPU time, like you're looking at a block or piece of processing, and you say, okay, the problem here is a high CPU time. Like, what could be the reason? So start by looking at like inefficient algorithm and or data structures. Like if it tells you, for example, this line is taking a lot of CPU time to run, because I haven't shown that yet, but what you can see is you can have a source view. Like that's the thing that sampler profile don't do, but that sampler profiler do, but instrumentation profilers don't, is they can show you the lines. That's the thing I wanted to show you with vTune, but it's not done yet. Oh, it is. Good. Okay. I will go back to it. Okay, cool. So, no, I don't want to learn about it. I don't want to learn about it. Thank you. Yes, thank you. There we go. So you can see a bottom up. So bottom up is basically the leaf nodes that take the most time. So it's a way to try to see if you all end up calling. Yes, I know about this. Thank you very much. That will tell you what is the most expensive. For example, you will see that the most CPU time I do is sleep condition variable. It's because it's using all the threads. So a thing I can do is say, you know what? For now, let's focus on the main thread because that's the main thing I care about. So it will basically recompute all the numbers from that view. Oh, okay, that's better. So we can see that the top thing we're doing is spending some time drawing some sprites on the screen because the Intel driver is really slow. Okay, that's a thing. But you see the bottom. You see like it's trying to find call stacks, function names under which a lot of your program is spent, basically, and that don't have a lot of very discernible detail under it. Function that costs you a lot. So obviously, render 2D3. We mentioned it before. I tweeted about how our UI system is not great recently, and I'm trying to fix it. It's due to the data model of it. You can see that updating the map is slow, and a bunch of other things. You can do the opposite. You can do a top-down tree, which starts at the beginning of the world, which maybe. Yeah, there it is. No? Come on. Thank you. So it starts here, blah, blah, blah. Okay, invoke main, run game, see application run, idle, okay. I'm gonna pull this a bit so I can see a bit more of the useful bits of the stack. Okay, so this is the update loop, update, and okay, 98. And you can go down and see, okay, here is where my CPU time is spent more and more. So for example, in my game, I'm trying to simulate the world. So 89% of my time is spent in trying to simulate an hour of time in the game. And you can see that 38% is simulating countries. 21% is trying to render because we're slower, where the CPU is too slow and it's trying to catch up the frame rate. And then the supply system, the AI, and then just about like maybe the air manager and everything else is just pointless. And then I can break it down. Again, way too much rendering, but updating the units is a bit slow. I'm doing a parallel 4 here, which I don't think it can explode. It should be able to explode it. Maybe it doesn't. Yeah, you can see that it's doing a parallel 4 and a parallel 4, blah, blah, blah. Yeah, it's doing, finally, it's a 4 each, cool. Now I can find the function. If you have TBB DLLs, I think it will fold all of that under like, you're trying to do some Intel stuff, I can fold that for you. So that's a bit more readable. Yeah, that's give you and another thing you can do, I can't do it here, but if you have the source, you can double click on a function, it will open the source, the source that was built with those PDBs, of course. It will open the source for you and it will annotate every line. I have a few screenshots later. With like, how much does this line take out of this entire function, which can help you if you're really trying to analyze one given function about why it's slow. So if we go back here, and for example, if one of those lines shows that that it has a high CPU time, you may have like an inefficient algorithm or data structure. You can have spin locks. You can have single-threaded code. That's also like a lot of CPU time. And you can have like then you can go back to like branch prediction, cache messages. We're going to try to delve a bit more into it. I have a bunch of screenshot profiles that will help us guide us. We can also have high wait time, which is usually due to synchronization or I/O. We'll delve a bit better into that. So if you want to filter a bit, because there's a lot of metrics, sampling views are like an aggregation of every call stack around every thread. As I mentioned before, you may want to filter on the bottleneck thread. For example, especially in the threading model for all games, it's the main thread does everything, and the other threads are just there to help it go faster. So if you want to see where the bottlenecks are, or you can, I can just filter on the main thread like I just did, and that's just give me an outline. Anytime this thread is slow, basically the whole process of the game will be slow. And if you have any kind of main thread or the equivalent of a main thread that is the one driving how fast the work is happening, this is your best way to see quickly what's the problem. And then if you have a work thread that you're trying to optimize, you can also filter on that one and say, hey, that's what I care about. Yeah, and I really like the 2D control flow view of instrumented profilers, again, the Optick and everything, because it gives me a very nice overview of what's happening, especially when it comes to threads. I don't think we saw it that much when I showed this one, because, again, I only have 3 cores and a half, but you can see that I have my worker thread here, and you can see that, for example, this computation here is trying to use several cores as a parallel force, so you can see that the other cores are also computing stuff. So it tells me, like, it can tell you very quickly, like, how much threads are you using, how many threads are you using, for example, for your computation is of a start for work. A bunch of the coming examples are taken from the candidates that apply to Paradox, actually, because the task, the first filtering task we got in our hiring process is to write a pathfinder, and it's great because it gives me hundreds and hundreds of good or bad pathfinders that sometimes I like to profile and get some cool results about it. All those ones are taken with permission of the people who wrote them. So a quick refresher on A*, just so we can explain the slides after this. If you've never done pathfinding with A*, it's a very common algorithm. You have an open set, which is like the list of, you're trying to path from A to B on a grid, for example. So you have an open set, which is the list of nodes you want to explore, like the ones you've seen so far, and you want to explore further around them to see if you can get to where you're going. Then you have the closed set, which is the ones you've seen already and explored, and you know you've seen everything around them, and you basically you're done. If you encounter again, you can just ignore them. You've already reached that place. There is no point in going there again. And so basically, what you do, you pick the best candidate to explore with some kind of heuristic. You explore its neighbor. You add the ones you haven't seen yet into your open set, and then you do it again until you reach the end, or there is no more thing in your open set, which means the result is unreachable. This is very basic. So, for example, here is a solution that got submitted to us a couple years back. So this is the main loop, which basically you can see it's trying to find the it's trying to use the A* thing. So it's trying to say, okay, find the next cheapest node to visit, which is what I explained, right? You have an open set trying to find the next best candidate, and as you can see. About 33% of the profiler and 40, like basically most of the time of the application is spent on those 2 lines here, 3 lines technically. And if you look at what this thing is doing, basically it's going through all the nodes in the open set and trying to find the one with the lowest score, which is better known as a linear search. And again, I mentioned inefficient algorithm. If you're trying to pathfind through a huge map and you potentially start getting thousands of candidate nodes in your open set and you're trying to go for the cheapest one every time, if you have to do a linear search every iteration, that's going to take you forever. So yeah, this is an example. You can fix it by by doing something smarter. How do you see that? Every time you're looking at a profiler and you have something that you have a lot of time spent in the loop, or a recursive call, or in any kind of like standard algorithm, it's consider, am I using the right algorithm for the job? Think about the big O. Like in this case, it's a simple big O. You're doing linear search. It's n. Every time you loop, you try to look through every possible candidate to see which one is the best one. There's got to be a better way. There is. I'm not going to give you the answer because maybe you will apply, but you know, a few tips for free. Yeah, another option, can the computations that are done be cached and maybe reused? If you do that, then you don't have to spend that much time computing things again. This is maybe the basics. Another thing that could be wrong is data structure. This is another submission. It's a lot of text. I don't want you to read all of it. You can just focus on the, and actually when you're profiling, you maybe not want to read all of it. Just focus on the right bit, which is total amount of CPU time in the whole application spent on this. And you can see like, those three ones, 15%, 18, 19%, 5%. If you look at the on the left at what they do, they're always accessing the same container. In this submission case, if I recall correctly, the person was storing, I think he has a standard map of every node he had seen so far, and basically how many steps it is from the start. So every time he was trying in the loop to, every time he was analyzing the neighbors of a given cell to try to see, hey, is it the shortest path to apply? Have I seen this path already? And how long is it? He was doing free lookup to this map. And as you can see, most of your time is spent doing like basically map square bracket operator. So the first one is trying to find the current cell, and the next one is trying to find the candidate, and the last one is trying to oh yeah, and the last one is trying to add the next thing. If you know anything about standard maps, you already know that this can be optimized. For example, current cell is not modified during the loop, so that call could absolutely be put one up, and you wouldn't have to do that many lookups. This find and this insert are basically very similar operation, because when you find, you can actually get a hint of where to put it next. So that would probably save you some time, because you wouldn't have to do a search through the map again to figure out where you would insert it. That kind of thing. Also, you could not use a standard map, because this is clearly not the best way of getting a good performance out of PyFinder. Another free tip. So yeah, inefficient data structure. How do you see that you have an inefficient data structure in your code? Well, if your profiler is telling you you're spending a lot of time on a find, or an insert, or a square bracket operator, there's a high chance that maybe this is not the best tool for the job. It is easier to spot in bottom-up if you don't have inlining, because if you build without inlining, then you will see at the top, bottom-up, the main thing is fine. If you don't, you'll have to actually find the functions that are doing it and then see where they call those methods. But it's still possible. Again, know your data structures and their strengths and weaknesses. Some are very good at some stuff and very bad at others. Some are just bad. Mostly, like list is mostly bad, for example. There's a few cases, but mostly bad. Vector is mostly good, with a few exceptions. If you have a spin lock, so if your profiler reports that you have a high spin time, usually sampling profiler are able to realize that the function is actually a spin lock. If you're using the ones in the standard, I don't even know if there was one in the standard, actually. I don't think there is. I see other people like frowning on the front row. Is there a spin lock in the standard? I see some no. There's no. Okay. But vTune is smart enough to detect that something is a spin lock, usually. Either because it's a CPU primitive or because, I mean, the code is really obvious. It's basically banging on an atomic or something like that. Yeah, if you have a high spin time, there's probably something that is not great. So usually it means take a step back and look at your threading model. Why are you spinning all the time here? Is there a better way to do it? There are a bunch of talks about concurrency. This is not one of them. So I would rather you go and watch one of those. There's a plethora of good options there. Single-threaded code, well, how do you see it? When you look at your timeline and the core usage is really low. Beware, if you start having 16 or 32 cores on your machine, it might be a bit over-ambitious of what's the ideal thing you want. It's not going to be showing very much on this one, But I think if I run vTune on my home machine, which has 16 cores, it tells me that if I'm on average using 15 cores, I'm kind of good, but not great. And I don't know what kind of applications you write, but if I can even use like 8 cores all the time, that's already very good. I think vTune is a bit optimistic there. You can tweak how much you think is good, but that's still a metric for you, right? If your average core utilization, which actually you can see, I'll show you here in the summary. Yeah. You can see like, this one is really bad, but I think it's because we're alt-tab and my Intel driver is dying. But you can see like, hey, how good it is. You can tweak those numbers. So for example, you can say, come on, ideal is not cool. Maybe ideal is like 2. So I'll do like this. Oh, it doesn't. I need to. Okay. You know, I accept this, for example. Okay. You can change the bar if you want, and then you can make a cool screenshot for people and then tweak which one is good. But yeah, that gives you an idea of how much CPUs are you using. And that gives you a hint that maybe there's something you can be doing. Again, this is not my talk about using many cores. I have other talks about that, and other people have other talks about that you can look at. But yeah, consider parallel algorithm. Obviously, if you have a very low core usage in your timeline, most modern CPUs have a shit ton of core that are just dying to be used. So yeah, parallel algorithm, task schedulers, there are options there. If you start delving even further, which again, I would say do not look at those metrics too early. Wait until you have looked at the other ones and still haven't found any good explanation for the problem. Then you can start looking at microarchitecture usage. I'm not going to do it now because I'm a bit, the time is a bit slow, and again, this is a whole topic by itself. But vTune and other providers can give you a lot of metrics, like the number of clock cycle it takes to execute a given instruction, and like why is it taking so many clocks cycle to do an instruction? Like for example, are you waiting on the cache? Is it is it waiting on, is it like a branch prediction is wrong, that kind of thing. Those are very high, there are way more advanced things that I would not recommend you start with, again, like third warning about it. But it's more and more important on modern CPUs to at some point start looking into them. Again, not early, get the big picture out of the way, but once you're there, you can get something interesting. Another word of warning, again, micro-optimization is hard on large application. It's tricky. That's the reason why I barely rely on it on my game, because I mean my game is considered a large application. Micro optimization works at its best when you're looking at a very small piece of code. Like if you can isolate something in a unit test, I would do micro optimization for like an engine structure, for example. I can write like a micro benchmark or unit test for, because then I have a very small hot piece of code that I can run and say, oh yeah, this thing is just very self-contained, and I can see what the problem is. This is way more usable than looking at a very huge code base that does a lot of things and then say, oh, you have a problem here. Like, you might be able to figure out a way to make it better, but it's way harder to reason, especially when you're trying to keep in mind like what's in the cache at a given moment. Depends on the machine, depends on how many functions you call at every line. It gets very muddy. But if you have a very small use case, then you can start looking at why do I have a very huge clock per instruction rate. There's probably something wrong. Either my data access pattern is bad, maybe there's branch misprediction, that kind of thing. Although again, like changing data structures and going back to thinking about which data structure is more efficient might be good enough. For example, if you're trying to do an iteration through a list, you will get a high CPI rate because you keep dereferencing pointers all the time, and that's really bad for caching, which is very bad for your clock per instruction rate, because you need to fetch data from main memory every time. If you replace it by a vector, because you have been told 20 times probably in different talks that you should use vector rather than list, that will go away, and you will not have to delve into the very fine details of why is my CPU slow on this particular instruction, which I would recommend. It's way less of a brain thing to do. Yeah, keep it for last. It's basically my key takeaway of this. If you see some blocking I/O, which usually you see it because you have a wait time or a sleep time or a system time on some network or file API. For example, if you remember my talk from 2 years ago. It was basically that. I had a bunch of wait time in various places. So can you think about asynchronous I/O? Again, there's a lot of resources about that, but I think it's the thing I had to tell another programmer recently. Do not load a texture in the main thread. That's bad. That stopped the application until I'm done reading on the disk. That's not efficient. It is really not. The disk is slow. Especially on Windows, it's terrible. If you have a long wait time on a mutex or a semaphore, this is a screenshot from my talk 2 years ago. This is the profile of the loading of the game. In Stellaris, before I made my optimization, there was 58 seconds of the loading time spent waiting on a mutex. That wasn't great. It was fixed. It was replaced by wait time on the disk, but I improved it, and at some point it started getting reasonable. But yeah, 58 seconds waiting on a mutex while trying. This is why the game went from like, I think 45 seconds to start to like 12. That was one of the reasons. Because that's across all threads. I think it's because the people who had implemented the loading thing at the time were using an old file system library which was not thread safe. So basically they added a mutex on every file system call, and then they replaced the library and did not remove the mutex. Happens. So yeah, high wait time on synchronization primitives. Remember, it should not be called a mutex, it should be called a bottleneck. And I can't remember if it's from the actual author of the mutex or not, or maybe somebody close to him would say like, I wish we had called it bottleneck instead of mutex. That would have screamed to people, yep, don't do it. Like, or at least consider you are introducing a bottleneck in your application now. It's not just like, oh, I have a threading data access problem, I'll put a mutex and be done with it. No, you put a bottleneck and you're done with it, which may mean you're not done with it. Consider changing your concurrency model. Again, this is a very broad and introductory talk to profiling and where to start looking forward. I could spend days talking about all the things you can analyze and where to go. Look up around. There's a lot of resources to help you look at how you can do parallelism and other things without using mutexes. So again, Profiler will show you what sticks out. You might need to do some filtering to focus on the right part. And at the end of the day, start by dealing with the the easier stuff, like inefficient algorithm, bad data structures, any kind of lock. That is the very obvious, like, oh, this is probably like architectural problem, code architectural problems. That's the higher level abstractions. And then once you've solved those, then you can start looking like, maybe the branch prediction isn't great and I can improve it. Maybe this algorithm should like access the cache differently. Maybe I have some weird like false concurrency, false sharing problems. Those are very interesting problems, but again, don't start there. Just start with the basics. So in conclusion, Profiler will help you pinpoint performance bottleneck. But again, domain knowledge is key, and it will help you speed up your analysis by a large factor, because you will immediately, something will scream at you when you look at the profiler and says, this is definitely not supposed to take that long. And finally, I would really recommend you add instrumentation support to your program. I think I've done the last game at Paradox a month ago. It's the oldest one we still have in production. They didn't have instrumentation since. I'm pretty sure, having worked on that one a while ago, something screamed at me when I looked at it the first time. So if you add it to your program, I guarantee you will find something. Because maybe that's the main thing I learned after trying to do performance work over the past couple years, is that it is insane. The amount of code you look at that starts in your profiler at like, I don't know, 10 milliseconds, and when you're done, it's like half a millisecond. Like, CPUs today are dumb fast, but it's also very easy to make them go dumb slow. And with profiling, you might be able to identify a bunch of those in your code and fix them. Oh, and furthermore, I think your build should be destroyed. So the question is, I think I should repeat for the recording. Somebody was looking up Optick already. I'm glad I already tried to convert somebody. And it mentioned C++ profiler for games. Yes, it comes from the gaming industry originally. It was made by people who really wanted it. So they have a bunch of features that will help you if you're doing games. Like they have a bunch of engine support, I think, for Unity and Unreal. They probably also have some like GPU things. It's made by people who work in the game industry, and people in the game industry are weird, and they think that the problem only applies to them. They're absolutely wrong. Everybody else has the same performance problem. They just think they're alone. So it doesn't mean that it's only for games. You can absolutely plug Optick in something else. So the question is, can it help you see code that is not executed? And I would say no. It's about what's recording about where the code has been going through, not what it hasn't going through, because it cannot really reason about it. You could probably try to have internal like assertions if that thing happens too often, but that's not really about profiling. I think profiling will tell you, hey, this is happening a lot, and then you can say, wait, this shouldn't be happening that much. And that way you can get back to the, oh, there's probably a cache that is actually not caching correctly. And basically being like marked dirty every once too often. Question is there a way to mark a branch, say I expect it to go there most of the time? Not for profiling as far as I know. Yeah, I suppose, yes. A suggestion has been to profile the other branch. Yeah, a thing you can do is Profiler allows you to do a free text search on like if I look at vTune, for example, if I go back here and you do color you have like all the functions here. So I could do a Control F, and for example, if each branch is a function call, I could try to look at both of them and see which one is taking the most time. And if one of them is like 80% and the other 20%, well, that's an answer. A better thing actually you can do, if they're both under the same caller, the caller callee will help you, because on the right side, it will tell you, hey, it's calling this function. Okay, this one is maybe not a good example. See sprite render? Yes. Yes, you can see, for example, it's doing two things. It's calling the like the meta type to render it, and then it's trying to also calling some rotation things. And it's 1% rotating, 97% rendering. If you had two functions that are like, sometimes it's one, sometimes it's the other, you could probably see like, is it the right distribution you're expecting there?